Dr. Hsi-Yen. He came from Livermore. He is an expert in the model output diagnosis. So he's going to talk to us about his recent work on this part. Please welcome him.
Hello, everyone. So the title of my talk is How Can We Use Short-Term hindcast Approach to Understand Systematic Errors in Climate Models. So first of all, I want to acknowledge funding support from the U.S. Department of Energy. This is the project I'm working on, the Cloud Associated Parameterizations Testbed, or CAP. And the CAP is led by both PIs, Steve Klein and Hsi-Yen, and also all my collaborators from my labs and also other modeling centers. You can see the names listed here. It's a collaborative effort. So, so the motivation of this study is, if you look at the future precipitation change, and this is the IPCC 5 RCP 8.5, and it's the result from 39 models, and it's the last 1981 average between 2081 and 2100, and minus the present day. As you can see, there's a precipitation change pattern over this figure. But if you look at closely, especially the region over land, where there's no either dots nor the dash hatch lines, suggests that there's a large disagreement in the model that suggests the sign of the change of precipitation. So what we really want to understand this large uncertainty in the future precipitation change, and also reduce the uncertainty of this. And what we want to do to achieve this goal is to improve our understanding of the moist processes, such as convection, clouds, and precipitation, and also their feedbacks in climate with observation or model simulations. However, if you look at the model performance of the latest climate models, this is the simplified AMIP. So this is not the couple model, just the AMIP run, multi-model precipitation bias from the northern summer. And as you can see, this large systematic bias, such as wet bias in most of the tropical ocean, and also the dry bias in the most of tropical land. And these large systematic bias are still present in the latest version of the climate models. So if you plot the same figure from CMIC 3, you actually see exactly the same pattern of the bias. It's actually a shame because we have been contribute a lot of effort on the model development, but several decades goes on, we're still facing the same issues. And it's not like we are incompetent, it's just the problem is too difficult to solve, at least for this issue. And we just we didn't understand this problem too much. However, if we still have this large systematic bias in the present day climate simulation, and this may affect the fidelity of the future precipitation projection. So, Edmund, should we just give up, or do we have any better ideas? Well, there actually is. So, in our recent study, so this is the same figure, except we just using one particular model, which is the community atmosphere model, version 5. And this is the climate bias. Is very similar to the bias you're seeing from the multi-model mean. So if you integrate the model in just a few days, this is the day 2 hindcast ensemble, and this is the day 5 hindcast ensemble. And the bias pattern from day 2 comparing to the AMIP bias is very similar, because as you can see, the bias correlation is about 0.71. And if you look at the day phi, the correlation can be as high as 0.8. And most of the precipitation bias is actually just showed up in a few days. And this is not just the precipitation. If you look at the cloud field and also radiation, you all show similar patterns. These biases are fast. It just showed up. So what can we? When we identify this correspondence, what can it tell us? Well, it provides some essential clues to the origin of the climate errors. So, for example, if we find there's a good correspondence, and this may indicate that the errors are likely the results of parameterization errors, because when we do the hindcast, we initialize the model with realistic large-scale scale. So even though we only integrated the model for 2 days, the large-scale state still remain close to observation. So what you really see in the error terms is likely due to the model parameterization. Well, if you get a poor correspondence, it also tells us something, and it tells us that these biases are likely due to feedbacks between the large-scale flow and the parameterized physics, because this bias didn't show up in a few days. Maybe it requires certain large-scale interaction for the bias to develop. So to look into this correspondence between the short and the long timescale systematic errors, here we have two studies. So this first one is using the community atmosphere model, version 4 and version 5, and we look in detail about the model bias. And also we look at several climate models, which is the transpose AMIP and also the CMIP by AMIP. The transpose AMIP is actually you just run the same AMIP climate model but in the hindcast mode. These are just the atmospheric only model simulation. There's no couple ocean simulation. So for the CAN4 and the CAN5 study, we focus on the Hsi. Hsi stands for the year of tropical convection, which is from May 2008 to April 2010. But here we only show the result from the 2009. So for this study, we use the CAN5 and we do the hindcast every day for 6 days. So here's a cartoon about how we do this short-term hindcast. So here for each select time period, for example, here is 00Z October 10th, 2009, and you have the initial condition from the ECNWF analysis, and then you do the hindcast for between 2 or 20 days based on your purpose. For example, if you look at the bias, you can just doing this for 2 to 5 days, but if you look at the tropical variability, such as the MJO, you can extend the hindcast to 20 days. So you do this every day. So you just do the hindcast, and then from the hindcast lead time 00Z to 24Z, you form the day 1 ensemble, and from 24 to 48, you form the day 2 ensemble, so on and forth for the rest of the hindcast duration. And now you have a bunch of hindcasts. And here we have the entire hindcast for the 2009, so we have 365 samples. Now, as I told you in the beginning, when we do the hindcast, the initial drift for the model, for the large-scale state is really small. Here is the example from CAN4. So this is a Taylor diagram. It shows you, and here's the observation. So when you compare the model field to observation, it shows you the pattern correlation and the pattern standard deviation. So for a particular field, if you close to the observation, which is here, then it means this field is better. And if you further away from the observation, which means the field is relatively bad. A few fields just stand out over here. Those are the total cloud fraction, and 2 represent the day 2 ensemble, 5 represent day 5, and 8 is AMIP. And all those 2, 5, 8s are the zonal wind temperature, specific humidity from either lower or upper troposphere. As you can see, even at day 5, these large-scale states still very close to observation. However, for cloud or precipitation, it just degraded very fast. So here we look at the precipitation annual mean bias for the 2009. This is the CAN4, this is CAN5, day 2 ensemble, day 5, and climate run. You can see the day 2 bias is very similar to the climate as I showed you in the beginning. And it doesn't matter for CAN4 or CAN5, both are show very similar results for the precipitation bias. There are also some interesting figure, for example, the double ITCZ people have been talking about. Over in the climate run, you do see this secondary ITC in the southern Pacific, but it doesn't really show up at the day 5, which suggests this feature may require longer time scale, require the interaction between the model physics and the large scale state. As you can see from both plots here, at least for CAN5 and CAN4. So we further look at the result from the transpose AMI and the simplified AMI because we only show the result from the CAN4 and CAN5. Is this correspondence robust across different climate models? And also if the correspondence is robust across all the models, maybe by improving the bias in one model, it can also improve all the models. So we have the short-term hindcast from the transposed AMIP, and we just choose a particular experiment which is focused on the July 2009. We have a 16 hindcast ensemble, and the long-term climate simulation is from the simplified AMI, which is the northern summer of 1979 to 2008. And we are particularly focused on the model moist processes. And here are the 5 models from the transposed AMI archive. This is the CCliCS4, CAN4, IPSL, HotGen2. For the HotGen2, we have 2 different initial conditions, but generally the results are very similar. And also CNRN and MIRAC5. So you can see we have models with different horizontal and vertical resolutions. So does the resolution matter a lot? The result is no. The bias is just showed up. It doesn't matter which resolution you use. So this is the simplified AMI multi-model mean precipitation bias in the color shaded. So this figure is very similar to the figure I showed you in the beginning. And also there's some additional information, which are these dots. And these dots represent that if more than 4 out of 5 climate models, if these bias just showed up in a few days, we just put a dot over there. So for example, for this region, if 4 climate model you run for the 5-day hindcast, and if at this point, if the bias sign show exactly the same as the climate run, and which suggests this bias, this systematic bias it just showed up very fast across all the models. As you can see, most of the multi-model mean precipitation bias just showed up. As you can see, most of the wet bias in the tropics ocean, and also the dry bias over the Africa. However, very interesting, not over the Western Pacific Ocean. And this is a cloud fraction bias. This is from the escape simulator. So what it means is you have the satellite observation with the escape satellite, and you also have some special code that you imagine you have a modeling world and you have a satellite flying over the modeling world and what it measures about the cloud fraction. So it's a fair comparison for the cloud because the cloud parameterizations in different climate models, they may treat them differently. And this way we can really compare the model results all together. So the same, the color shade is the multi-model mean cloud bias from the climate run. And for the dotted region is is also if these biases just showed up in a few days. As you can see, most of the cloud bias showed up very fast. And also it suggests that most of the region have this underestimate of the cloud bias associated over land, such as the Eurasia continent and the North America continent. And this is also the same for the net shortwave radiation at the top of the atmosphere. And this is also linked to the simulated cloud fraction. I also linked to the simulated cloud condensate. As you can see, most of the bias also showed up in a few days. And also this negative bias may also imply the pure simulation of the cloud condensate, because we have previous plots, we have the we have bias low cloud fraction. However, here we actually have the negative cloud condensate simulation over here, and that's why we have this negative net shortwave radiation. Okay, so just have a quick summary of what we have shown here. So understanding over what time scale these systematic errors develop can yield significant insights into the origin of these the errors. And also the transpose emit model indicate that many systematic errors, particularly those associated with moist processes, are present in just a few days of the hindcast, or we can call these very fast processes. So with that in mind, and we in our study, we found additional interesting things. If you look at the surface air temperature, so this shows the surface air temperature, or the T2M bias for the northern summer. You can see this large warm bias over the Eurasia continent and also North America continent. Well, you can say that because we initialize the model with realistic temperature, then why we have this large bias near the surface? Now remember, we have this shortwave radiation bias and the cloud fraction bias. So we have too little clouds over the continent, and that suggests we have too much incoming shortwave radiation reach the surface. So the surface just heating up very fast because of the bias in the cloud and radiation, and that's one possibility. And also maybe another possibility is if you know how the 2 meter temperature is predicted, it's actually predicted through the land model. So if you have a bad land model initial condition, it may be the cause as well. Yep, here's what I just said. So you have initial precipitation bias, less precipitation, less cloud, and too much incoming shortwave radiation, and model the boundary condition, boundary layer property, and have a higher temperature, and also the bias in the initial condition for the Lens-Simpson model. Now, to really understand this warm bias problem, here now we identify this correspondence. Then the next step is we try to understand what caused the bias. So we have this intercomparison project. It's actually just announced. It's called the Clouds Above the United States and the Areas at the Surface. It's quite a clever acronym. It's actually not came up by me. It's by Cyril Mockcraft from the Met Office. It's called CAUSES. So it's a joint gas DOE, RGC, and ASR monitor project with the purpose to determine the role of the radiation and precipitation errors in temperature bias in climate model. As you can see, this is just the figure we zoom into the North America continent. You can see the bias is large, almost as large as 7 degrees Celsius. So the research focus, we have two focus. One is the radiation error, particularly due to the clouds, and this will led by the Met Office. And another is look at the precipitation and surface energy budget, and you were led by our lab. And so the method of this project is we're gonna use to look at the error growth in the hindcast mode, even with very fine resolution models. So why we care about this 2-meter temperature bias? So here is the here I plotted the signified historical 2-meter temperature bias in the central central North America. And also here is the signified RCP 8.5 warming. As you can see, we got a pretty good correlation between this historical temperature bias and the warming. So really, if you can reduce this bias in the 2-meter temperature, you will increase the fidelity in the future projection of surface temperature. And here's just a simple cartoon tells you what are the processes that will affect the surface air temperature, such as the radiation, surface albedo, or the surface turbulence fluxes, and also the ground heat flux. All these, any process that can affect these fluxes will affect the surface area temperature. So here, from past study, here are some hypotheses. The potential issue includes like the diurnal cycle of convection, or the organization or propagation of the convection, or the timing of precipitation, or how much evaporate, or the radiation impact on the convective core, the train cloud, or envelope, shell convection, surface flux, soil moisture, or other things we don't know yet. So we have 4 scientific questions, and in the next few minutes, I'm gonna focus on the last 2. And we're gonna look at, well, the question is, we're gonna ask is, does this atmosphere provide the correct amount of precipitation for the soil? Remember, I'm gonna focus on the precipitation and surface energy budget. And the second question I'm gonna ask is, does the surface energy balance reveal signs that evaporation is underestimated due to the lack of soil moisture? So here's our model experiment. So we use the CAN5 final model dynamical core in 1 degree. And we have 2 sets of 2-day hindcast. And we only focus on the northern summer, which is the June, July, August of 2008. And in these 2 sets of hindcasts, we use the same initial condition for CAM. And these are from the Hsi-Yen analysis. However, we use different CON initial conditions. Because in the past few slides, I mentioned maybe we have this large warm bias because we have the bad CON initial condition to start with. So we want to test that. So our analysis will focus on the day 2 ensemble for this US summertime warm bias, which is average over 24 to 48 hours. And so there are several ways to generate the CON initial condition for the hindcast experiment. So here I call it control is our usual way to do this. So you use the nudging method, and you nudge the model towards the reanalysis state variable. Now we later found out that if you nudge the state variable, for all the state variables, the U, V, T, and the Q, the model actually produces too little precipitation, which result in the low soil moisture in the model. And to solve this issue, we also have additional run, which is the initial condition generated by the offline COM simulation. And this simulation is forced with observations. And this is from the geodesic analysis data from January 1st of 1950. And technically, we just save this restart file from the CON as our initial condition. Okay, so here's the result. This is the difference of the 10 centimeter soil water difference at day 2. So the magnitude is here. Probably you don't really know how large is this. So if I show you from this particular point with observation, this is the in situ observation from the DOE arm site. So the black line is the observation, and the blue line is from the geodesic run, and the red line is from the control. So you can see that, and there's a significant increase in the soil moisture in the geodesic run, and it's closer to the observation. If you even consider the uncertainty in the observation, this is actually pretty good. And as you can see, this one is almost twice as the original control runs. So we do have the low soil moisture in the control. And this is quite large. So what happened to the surface fluxes and the surface temperature if you have this large difference in the soil moisture? So as you expect, when you have difference in the soil moisture, you have large difference in the surface latent heat flux. This can be as large as almost 30 to 40 watts per meter square. So this is the geodes minus control, so you have more latent heat flux and less sensible heat flux. And the combination of these two contribute to a cooling in the southern Great Plain. And this cooling can be as large as 4 degrees C. And this is just the soil moisture from the previous plot. So you can further compare these fluxes and the temperature with the observation. So here's again the arm side observation for the first one is the precipitation. Second one is the temperature, surface air temperature, latent heat flux, sensible heat flux, and the non-surface radiation. And you can clearly see that the large differences mostly come from the latent heat and the sensible heat flux. So in the control arm, you have too little latent heat flux and too much sensible heat. And actually the net surface radiation doesn't change too much. And that's the main reason that you have this large difference in the surface air temperature. And also interesting, even though with this large difference in the soil moisture, the precipitation actually doesn't change too much. That's probably because when you start with the hindcast, you start with exactly same atmospheric profile. And even after day 2, this profile is still very close to each other. That's why the entire column of the moisture are very similar in these two runs. Now we further look at the 10 centimeter soil moisture. And this is the precipitation. So the black line is from the observation. And again, the blue is the geodes run, and the red is the control, the dry case. Now, if you start another hindcast from the beginning, from the January 1st, and you let it run free, so you start exactly the same initial condition as this run, and you run it free. And this is the precipitation again, probably maybe you cannot see it very clearly, but around 30 days in this free run, the precipitation compared to observation is really low here, and also the soil moisture just decreases. So it seems when you let the model run free and the model start to dry out because you don't have enough precipitation to maintain the soil moisture, and then results in higher sensible heat and lower latent heat fluxes. And that's why you have this huge surface area temperature. So to have a quick summary for this part of the study. So in the beginning, we asked 2 questions. Does the surface energy balance reveal the signs that evaporation is underestimated due to the lack of soil moisture? The answer is yes, as we can see from the model simulation. And this is likely the cause of the surface water temperature bias. And also, does the atmospheric provide the correct amount of precipitation for the soil? And the answer is no. As you from the free run, as you can see that even though we use stuff with a relatively correct soil moisture, the model still dry out because you don't have enough precipitation. So then what is the source of this lack of the precipitation? And some suggestions are like the organization, like the mesoscale convection system, or the propagation of the convection from the Rockies, which cannot resolve in this model resolution. This is the 1 degree model. You really need fine model resolution to resolve that. And actually, from another initial analysis by the Met Office group, it actually showed that the can that generate the largest bias is under those convective systems that you don't have enough clouds. Okay, so the take-home message from today's presentation is, so it remains challenging to improve this systematic bias in climate model simulation. Although here I shows the precipitation, but also as I told you that the systematic bias in the surface temperature can also affect the future projection of the surface air temperature. So this problem is difficult. However, it seems by using the short-term hindcast approach, this can at least provide some guidance to a better understanding of the underlying problem or underlying causes. So I will stop here and take questions.
Questions?
I really like the acronym CCliCS. So I'm wondering if you would allow more participants from the land surface modeling community. I understand this effort is mainly initiated from the atmospheric modeling community, but in the past, land surface modeling community has been really active to understand the uncertainties in simulations of a surface soil, like soil moisture, and the partitioning of runoff, precipitation into runoff and evapotranspiration. We have been doing that in many years using observed forcing. But now when we link land surface to atmosphere, when the forcing not observed, you have sources of uncertainties from both ways, from land, also from atmosphere. So I'm wondering how you see now the atmosphere community recognize this. Because in the past, atmosphere community neglects, ignores the work done by land surface modeling community. Now gradually you recognize the work. So how do you see the more stronger collaboration between land and atmosphere?
I guess definitely we need people from the land modeling community. Actually, when we in the initial phase, when we developed the model experiment, we also include some people from the locals group or the GLASA group, and but it's a little bit difficult to to combine both experiment, like the full on certain aspects, such as you said. We can have additional experiment, but so far, all these runs in the interconference project has to go through this cover run. We do really interested in those offline runs. As you actually recently, I also collaborated with Livermore. We also did some offline run, but we had to discuss about details. We can talk about that offline.
Other question?
So one question. The arms observational soil moisture profile look quite smooth compared to that even for precipitation data. Do you know what happened for the 10 centimeter observational soil moisture? Yes, something like this.
Yeah, well, the result I showed here are on the daily mean, so it's not actually.
I guess the question is why the model has such large variability compared to observation.
I think that's some precision
Events.
But it seems that the observational data doesn't capture that. Really can see from the model.
I should suggest the level precision is the source of error, right? So, for example, for this one, precision is precision level test, what kind of precision it can generate? Simply because the convection of the cycle or the weak moisture transfer from the Gulf of Mexico?
Yeah, so well, I know that the low level jet, but at least in this model relation, you cannot really resolve that. It starts with so much moisture field in the atmosphere, but because the model wind may not be as strong as it's supposed to be. And that may be one reason. Another is, as I said, in the over here, visualization, mesoscale organization, I cannot resolve this one. I know that people shows like this accordingly, so you can get observation. Even want me to say about tonight, and what going into
with your hindcast on the understanding the MJO things.
So in the hindcast model, there are two types of hindcast. One is doing 2 days, 2009, and one going into 2010. And so that in the hindcast model, there are two types of hindcast. One is doing 2 days, but you output the model data every time. So that in the hindcast model, there are two types of hindcast. One is doing 2 days, but you output the model data every time step over the native model read. And also you have additional step, which is you do the hindcast everyday data every time step over the native model read. And also you have additional step, which is you do the hindcast every day but for 20 days. So you can sort of compare the result between the day 2 and the day 20. And
So we got similar conclusions like convective parameterizations causes all the problems.
it definitely the problem is in the multiplics. For example, classic theory is so before the surprise stage you have this shallow convection that in the multiplics. For example, classic theory is so before the surprise stage you have this shallow convection that in the transition stage you have this shallow convection that more theory is so before the surprise stage you have this shallow convection that in the transition stage you have this shallow convection which is kind of missing even in the first few days of hindcast. Yeah. And model tend to do poorly for shallow convection as you know very well.
Can I comment on this MU stuff?
Okay.
Actually, so it's based on the comparison result of this 20-year limit simulation, also under Yachi project. Actually, it's not conclusive result for the convection or whatever.
Okay,
The
that's
only
even better.
conclusion is the coupling can help.
Oh,
Yeah.
good to
There are
know.
people that submit to still kind of thing.
Yeah, I was actually on 2 of the papers. I was the co-author on 2 of the papers, and it's quite interesting because we submitted a result using CAM5 with different convective microphysics scheme. And the CAM5 is very interesting because it does such a poor job in the climate MJO simulation, but it actually does the best MJO forecast if you start the right profile of the atmospheric humidity, temperature, wind. And you can get very good MJO even after 20 days, you can still see it.
Okay. Okay, let's send our speaker again. Our next speaker is Dr. Miura from Tokyo University. Dr. Miura is an expert in numerical modeling and as well as the MJL. We discussed a lot. So he's going to talk to us about his recent studies on the global cloud resolving model, Nikon. Let's welcome him. Just a moment, please. Okay. Just a moment, please. Just a moment, please. I'm Hiroaki Miura from University of Tokyo, and at first I'd like to thank Professor Hsu and Kemin Hilder for giving me a chance to have a talk here. And he introduced me as an expert, but I'm not so good at modeling and other things. Anyway, today the title of my talk today is Recent Studies Using a Global CRM. And at first, I'd like to give an overview of the non-hydrostatic ixhedral atmosphere model. And at first, I'd like to give an overview of the non-hydrostatic ixhedral atmosphere model Nikon. And after that, I want to introduce some of the recent and future updates of Nikon model, and some of the things that I'm working on now. I mentioned from the simulation using horizontal mesh size less than 1 kilometer, and the other is an MJO stuff. Anyway, first back to the cloud parameterization issue. And as you know very well, the cloud parameterization framework is very valuable to test our knowledge
or understanding about the nature of clouds. And we still do not understand how strongly the clouds are controlled by large scales. And also how strong the cloud's feedback to large scale is, of course, an unknown issue. And the cloud parameterization assumes an artificial scale separation for the spatial scales that there is no separation in nature as it was confirmed from observations. For the spatial scales that there is no separation in nature as it was confirmed from observations. So that is, there are a lot of remaining issues around the cloud parameterizations. Anyway, that is an interesting problem, but in terms of numerical modeling, that is a very, very strong cause of uncertainties in climate simulations. And Dave Randall called it as cloud parameterization deadlock in 2000 paper. And he published a paper titled Beyond the Deadlock last year, and he gave an overview for these past 10 years activity to overcome this deadlock. And one important activities in the last 10 years, maybe the super parameterization or the multi-scale modeling framework. The first trial was done by Dr. Grabowski in 2001. And at the same year, Marat and Dave Randall published a very similar approach in a letter. Anyway, the super parameterization uses a cloud resolving model, 2D or the very small size 3D model inside climate model in place of conventional parameterizations. And the other approach to overcome the deadlock may be our high resolution modeling activity. Dr. Mazno is very famous for his equatorially trapped wave theories. And he is also very famous for his theory for the stratospheric sudden warming. And he is still alive. And he's now not working on the methodology for his theory for the stratospheric sudden warming. And he is still alive. And he's now not working on the methodological field. He's now working to develop he is still alive. And he's now not working on the methodological field. He's now working to develop equation sets for plate tectonics. And he wants to predict earthquakes in future. He do not think that he can do it within his lifetime, but he is very enjoying about that now. Anyway, he wants to have a model that can simulate spontaneous behavior of clouds about 10 years ago. And that model requires horizontal resolution less than 10 kilometers to avoid cumulus parameterization issues. And Professor Sato decided to realize his dream 10 years ago with Dr. Tomita, who is now leading our group in CCliCS, where the K-computer is. And in my point of view, Professor Sato is a strong leader, and I respect him, but mechanical dynamics core are coded by him more than 90% or so, I think. And I want to mention, before going to my study, the cross-zoning model cannot solve all of the issues related to clouds. Here I show many uncertainties in climate models, in conventional climate models, and cloud-related quantities are not simulated. Cloud area, as somebody mentioned in the morning talk, cloud area is not simulated explicitly in the model, and this height and figure flux are all important issues in cumulus parameterizations, and other processes are important. With using cloud resolving approach, we can compute these quantities at least explicitly. I don't want to say that these quantities are exactly or correctly simulated with this model. We can simulate or directly compute these quantities in the cloud resolving model. And so that fact may benefit us because, for example, the cloud area, by computing cloud area explicitly, we can estimate the cloud radiation interaction explicitly. I do not want to say it's correct or not. And we can compute direct interaction between clouds and cloud issue. But with cloud system resolving models, entanglement, determinant, turbulent issues remains, and the microphysics issues are another deadlock for our cloud resolving our global climate simulations. And turbulent mixing in the low clouds is also still an important problem. And all these processes controls the dry or moist in the free troposphere, and this is very important to have good climate simulation. So in back to 2002, when Dr. Sato started the development of NICAM, the Earth simulator was developed in Japan, and it was ranked in the first place of the top 500 list. And 12 years have passed since this time. 12 years is an important unit in the Eastern Asia anyway. And this is 12 years ago. And at that time, not only the NICAM, but also the microclimate model is benefited from this computer. The horizontal resolution was increased from 240 to about 100. And that was the highest resolution model is IPCC AR4. And when we started, this is just a historical overview about our knowledge about that time, about the dynamical core development. In this age, we thought, or we believed that the spectral method would die in near future because of the high computational burden of the Legendre transformation in high-resolution simulation on massive parallel machines. But we now know that the ECMW spectral model is fast even for the T8000 on parallel machines. And the other thing is that there was only one icosahedral grid model at that time. That is Z-grid, that predict vorticity and divergence. And it requires Poisson solver to have velocity potential and stream function to reconstruct velocity field. And Poisson solver, we believe that Poisson solver also do not work on massive parallel machines.